So, welcome back for the one last time, last lecture of the course, and which will be on elastic contact instability. I will try to wrap it up a bit fast and then have a quick overview of the course. Let us see how time permits. So, we were talking about contact instability, and the idea now we are discussing is, can these elastic instability structures be aligned with a topographically patterned stamp? And our expectation is that if one takes a, let us say, a grating pattern stamp, one would expect the interfacial interaction to be active over these areas, and therefore, it is expected that probably a positive replica will happen. Let us see what actually happens. So, here is a sort of a composite picture that will give you a detailed idea about what is happening. So, here is the true AFM image that is obtained in experiments. Here is the sort of the contactor, which is initially far away from the film, and here is in fact a zone where in the form of schematics I will try to emphasize what exactly is happening. So, initially the contactor is approaching the film, it is still far away. So, therefore, there is no interaction, and then you see the first signs of interaction, as you had seen in the video I was showing in the previous class, was in the formation of columns. For a flat contactor, the columns were completely random, but here you see that the columns are not random, but they form, they are sort of aligned and they form only below the stamp protrusions, which is logical. You approach further. In fact, the strength of the attraction between the film and these areas, the protrusions of the contactor sort of increases, and as a result more number of columns appear, as well as some of the columns which have already formed, they sort of tend to get stretched along the direction of the contactor protrusions, and as a result you do get a positive replica of the stamp. How do you know that you have got a positive replica? One quick answer is that the height of the features here do not match the height of the stamp, and which is possible, particularly if it is slightly higher, it is only possible if it is a positive replica. In a negative replica it is not possible. Then of course, one knows that if one goes on pressing, one will eventually, this will become an embossing process. So, one will eventually get a negative replica. So, what happens then if the film at the stage where a positive replica has formed on the film surface, the contactor is still pressed, and if you press that, please do not forget that these replicated stripes themselves are soft. These are very soft, they are not permanent, they are still in the elastic stage, they are soft, and you press them from top. So, what happens is, now these stripes starts to exhibit undulation, lateral undulation, which is also very logical. But what is very interesting is that these patterns have a periodicity of 1 micron or something like that, or 2 micron or something. So, they are pretty close to each other, and now the bulged out portion of the adjacent undulations, they are very close to each other, right. And again, what is a good number? When they are in the range of active van der Waals interaction, because they are after all interacting in air, so there is no chance of any repulsion, these undulations simply join up, and therefore, what it forms is an array of holes, which in fact you have seen in the context of duetting. There was a pattern directed duetting video a few lectures back where I used this, we used this identical substrate was used. But what is the real novelty of this technique from the standpoint of patterning? You start off with a grating pattern stamp, and then you create an array of holes with 2D order. So, this is the real advantage, or this is the real novelty of cleverly utilizing elastic contact instability with a pattern stamp, and this technique is known as elastic contact lithography, really rare capability of obtaining 2D structures starting from a 1D stamp. There are of course, beyond this stage, if one continues the approach, one eventually gets a perfect negative replica. There are certain conditions under which this perfect replication takes place, and one of the condition is the periodicity of the pattern stamp, that is lambda p, and you have a flat film where the thickness is h. Therefore, its natural length scale of instability is 3h. So, these type of picoliter beaker formation or array of holes occur only when lambda p is commensurate with lambda. So, in other words, if you have a stamp with lambda p equal to 3 micron, your film must have lambda equal to 3 micron, and which is possible only when h is of the order of 1 micron. If there is a mismatch, in fact, this type of secondary instability and their joining up is not observed. In fact, these are some of the images where there is a mismatch. There is a bit of science into it, but I will not go into all the detail. So, here you see the extent of mismatch is very less, and therefore, the beaker formation or the hole formation has taken place, but they are distorted, they are not that well ordered. These are cases where there is a significant mismatch, and therefore, I will stay away from commenting on that. Of course, one can also use in a bit clever way a flat contactor and a patterned substrate, because only a couple of lectures back in the context of spin coating on a topographically patterned substrate, we have discussed that on a topographically patterned substrate, if you have a continuous film, on a topographically patterned substrate, in fact, leads to a film with undulating top surface. So, what happens is this. So, you have a topographically patterned substrate, and on that you have a film, and there are undulations. So, if you now bring in a contactor from the top, the interaction is favored in these areas as compared to other areas, and therefore, you get the spatial variation what is essential to impose order to this type of a completely isotropic structure. So, here I mean the image sort of shows the variation to be too small, but these are the areas where you have a preferred attraction as compared to the other areas, and as a result you can again see here. Of course, one needs to understand the final conformal morphology will be a flat film because the contactor is flat, but at an intermediate stage one can again see this beautiful array of these 2D holes forming when there is of course a commensuration between the periodicity of the substrate patterns in this particular case with the film thickness, and one will understand what film thickness is one talking about. It is essentially the effective film thickness, right. So, this way of course, since you are looking at the atomic force microscope images, and this is the evolution sequence. So, you have an initial film with undulating top surface, then initial manifestation of instabilities with the formation of pillars, then positive replica, and then something this, and then complete conformal contact. Again here also this perfect ordering happens only when there is a perfect commensuration between the two, otherwise there is distortion. For example, here the thickness is much more, so you again see those labyrinths, but because of the presence of the substrate patterns, you see the labyrinths sort of tend to get a bit digitized. I mean they are sort of bit aligned, but in no condition you can say that the structures are aligned or well ordered. Sort of the last thing that I would like to emphasize is that while I was talking about elastic contact instability, I mentioned one thing, that there is a hysteresis. In fact, as you try to debond the film, it also undergoes morphological transition. The morphological transition sequence is exact opposite to that observed during approach, but more importantly, as we discussed, that during debonding the film sort of, there is a hysteresis, and the separation distance at which the film snaps off is in fact higher than the separation distance at which the initial contact is established. This can be attributed to pinning, maybe the film, when as the film comes in contact with the surface, it might be forming some pinning, strong pinning with the surface. There might be other reasons. In fact, one can argue it to the elastic stiffness of the film. There are a lot of theoretical formulations, for example, and Sarkar and Sharma in fact have worked out a kinetic pathway which shows why this hysteresis exists. Again, I will not go into the theoretical aspects, but what it means is that this in fact is similar to pulling something out, then stretching it, and the idea is that if you can freeze the structures of these stretched structures just ahead of detachment, you can sort of come up with a very, very novel concept of creating structures which are taller than the original pattern. Now, that is fascinating, because in the context of this stress relaxation based elastic recovery lithography, we have seen that using a single stamp, it is possible to create patterns with different feature height. In the context of elastic recovery lithography, or ERL, single stamp utilize stress relaxation to get patterns with different height. All this we have achieved, but the limitation is the height of the patterns varies between 0 to 80, where stamp height is 80, right. And you now know adequate amount of soft lithography, nano imprinted lithography, etc., etc. So, you know that any of the properly executed lithographic techniques, it is possible to create a perfect negative replica where the height of the replicated structures will match H0. But can you think of a technique that can create structures which are taller than H0? And the answer is, till date it is not doable. In any case, you have seen that high aspect ratio structures or tall structures are very, very important, if not anywhere else, in case of Cassie state of wetting, because Cassie state, achieving Cassie state necessitates achieving high RF, and for attaining high RF, one needs to in fact have high higher height of the features. Even in classical photolithography, if one would want to make structures which are high, one would require a thicker layer of photoresist, and then you know that there are a whole lot of problems that will crop up, because as the photoresist layer becomes thicker, there are issues going to be like exposure and all that, whether it will be uniform across the thickness, etc., etc. But here we are, I would again like to highlight, and this is a completely recent development. In fact, there is a possibility that during the debonding stage, the structure or whatever patterns form, they get pulled up, and if one can freeze them just ahead of detachment, one can in principle create structures that are taller than the original stamp pattern. And so, here are some images that gives you an idea of something more interesting, is that though the instability length scale, the wavelength, is independent of the shear modulus, it turns out that this debonding, the maximum height that can be achieved during debonding, that depends on the exact shear modulus of the film. In fact, it is in this range where for all the film thicknesses you see the debonding height is maximum. Of course, these experiments are performed with flat stamp, therefore, there is no ordering, but you can see from these images, for example, that a film with this particular shear modulus 0.075 megapascal, the debonding height of the patterns is 350 nanometer. In contrast, if mu the shear modulus is if the shear modulus is 0.43 megapascal, then in fact the height is about only 180 nanometer. And in both the cases you see that the initial contact, very carefully performed experiments, the initial contact is established when the separation distance is of the order of 60 to 70 nanometer. See, so this is in fact an indirect or a very direct validation that these van der Waals forces between two surfaces sort of stretch up to about 100 nanometer, maybe slightly less than that. So, there are certain theoretical formulation by Professor Sharma's group, which in fact suggests that as mu decreases, the snap off distance in fact increases. There is a physical review latest paper in 2004, which in fact gives this. I will not again go into the details of this, but it is already there. So, in principle, now by taking elastic films of different shear modulus and by utilizing their debonding or sort of freezing the patterns just ahead of detachment, in principle it seems like it is possible to make structures which have different feature height and which are tall. But with a flat contactor it does not make any sense, because the structures are random, and of course, there is a clue that yes, during approach contact is established at 70 nanometer separation. So, the structure height is only 70 nanometer and during debonding it goes up, but the real strength can be achieved only when a pattern contactor is used. And now everybody knows, based on all the concepts of elastic contact instability, that in order to achieve structures at the length scale of each pattern, you need to have a perfectly commensurate structure. So, one chooses a film according to film thickness according to the periodicity of the stamp available. So, this is the whole sequence. So, you can see that initially you see a positive replica, then eventually a complete conformal contact, a negative replica, and then you try to debond. Then what would you expect? What would you expect is that one interesting thing or difference from that of the, what is different from that of a flat contactor is in fact the film, the replicated patterns are in fact pinned in a stronger manner inside the grooves because of the presence of the surface walls. So, when you pull it up, those areas sort of get stretched like this, because I will just redraw. So, this is one groove, and here the film has formed also from this side. So, these areas of the film, because of the presence of the side walls, these side walls sort of act as a clamp and pull the film up. Therefore, the first cavitation in fact takes place below the stamp protrusion. So, if you have a stamp protrusion like this, the first cavitation in fact takes place here. While it is important to note that during approach sequence, the first patterns in fact formed below the stamp protrusions. So, with a pattern contactor, there is not only you can sort of in principle create tall structures, which I have not discussed, but you can imagine that one can do that, but there is also some sort of a difference in the pathway between bonding and debonding. If you look into this figure again and carefully, then that becomes very clear that during approach your first structures appeared below the stamp protrusion as expected, here, but during debonding the first cavities also appear at these areas. And then one can this is simple result that you vary the shear modulus, exact shear modulus of the film, and you sort of reduce the cross linker concentration. One can attain patterns which are 300 nanometer high using a stamp that is only 100 nanometer height. So, this is no longer a negative replica, it is not even a positive replica, it is some sort of a stretched replica. Of course, before detaching the stamp you need to freeze them. There is of course another concern that this is after all a stretched elastomer. So, are the structures permanent, or they are going to sort of relax out very soon. Experiments over a prolonged period of time shows that the structures are permanent. So, this in fact paves the way. So, this goes by the name elastic detachment lithography, because you sort of exploit the physics of debonding in a very clever way. This in fact is sort of the first evidence where tall structures can be created using a shallow stamp. One can in fact utilize this, something I did not mention in the context of elastic contact lithography, but maybe I will just touch upon so that you can enjoy the excitement. One can in fact, so of course, this particular case where you see you have chosen a film thickness where lambda p is equal to lambda equal to 3h, so that patterns form below each stamp protrusion. Now, if there is a mismatch, if your lambda is higher than lambda p, then what happens? Lambda is higher than lambda p means h is such that 3 times h is greater than lambda p, it sort of exceeds that. What happens is, even in this particular case, the elastic instability structures sort of rather faithfully obey their natural length scale of instability. So, you actually get structures like this. So, these are the bigger structures, and this obeys the lambda equal to 3h. So, one single structure spans below several of the stamp protrusions. So, and this periodicity matches lambda equal to 3h, which is fine. In fact, this gives a route for creating wider structures from a stamp with narrower features, that is fine. But what is more interesting is, now if you debond, right, the areas of the film which are in contact with the stamp sort of detach in sort of steps over the stamp protrusion, or it sort of goes into a gradual detachment mode, and that allows you to create structures. So, as one sort of pulls the contactor upward, the structures become progressively taller, and additionally they become narrow. So, we had talked about duty ratio. So, here under this particular condition, which apparently is not commensurate for creating structures, because there is no commensuration, you can not only create tall structures, but using a single stamp, by varying the extent of detachment, you can create structures which have different duty ratio. So, that is sort of all that I wanted to teach in this particular course, and let us see what are the stuff we have learnt. So, we had a pretty longish introduction. So, you should be now knowing what is nano and what is unique about the nano, and particularly what should come out from this particular course is, apart from the quantum size effect, in fact the length scale of 100 nanometer is very important, because between two surfaces, that is the range where van der Waals forces remains active. So, that leads to issues related to spontaneous instability in films. Of course, we are talking about the liquid films here, and we also talked about utility of nano pattern surfaces in creating super wettable surfaces, hydrophobic surfaces, optical color and things like that, and yeah, that is what we studied in introduction. Then we moved on to the basic concepts, where we understood surface tension and its components in a bit more detail, and we realized that even van der Waals force is responsible for major part of surface tension also. I mean, surface tension invariably has a signature of van der Waals forces. There can be other equations like other factors like polar interaction or steric interaction, which may also contribute to surface tension. We talked about wetting regimes like Cassie state and Wenzel state on a pattern surface, and we talked about Young's equation. We now very well understand what is a hydrophobic surface, what is a self-cleaning surface, and stuff like that. And then the additional new thing that you have really learned is Laplace pressure, that is across a curved liquid surface that there is a pressure gradient. Then we talked about patterning techniques. In fact, this has been split into 2 modules. So, one of the modules is photolithography, the other module is soft lithography. We had really detailed discussion on these, so I am not repeating. You understand photolithography is a specific technique. In fact, the whole progress in microelectronic industry relies on that. But in contrast, soft lithography is a suite of polymer specific techniques, and there are various varieties, and you can create a chemical pattern, you can create a topographic pattern, whatever. Then of course, you have created the patterns, but you need to sort of visualize them, and that's where the utility of your atomic force microscope comes in. So, we realized or understood how the AFM has evolved from the discovery of STM. AFM in fact, in many ways has changed the perception about vision, because AFM never captures a picture, it generates a data file. And towards the end, in fact, we talked about spontaneous instability and duetting of a liquid film, and then the issues related to that. Theoretically, under what condition a film becomes unstable based on spreading coefficient as well as based on effective interface potential. We talked about experimental evidences of how the morphologies evolve, formation of rim and things like that. And then we also talked about duetting of a bilayer, where there are extreme complexities because of the coupled deformation of 2 deformable interfaces. We talked about pattern directed duetting, and while talking that, we in fact talked about spin duetting as well, duetting during spin coating and creating structures based on spin duetting. This is one area that I could not cover in greater detail. I wish I had some more time to cover this. This is this phase segregation and demixing of polymer blends. It's a huge area, but I just gave you some glimpses of that. And finally, in the last phase, we talked about the elastic contact instability, the short wave nature, lambda equal to 3h, and how the patterns are made permanent, and the techniques like elastic contact lithography and elastic detachment lithography. While we were discussing soft lithography, we had talked about elastic recovery lithography, hydrogel based shrinking, and now elastic detachment lithography in this particular lecture. So, that sort of concludes my course. These are some of the key images and terms which should remain impregnated into your mind now that you have attended this course. For example, this one will always remind you of a drop sitting on a liquid surface and the Young's equation. This is the Cassie state, and from now onwards, Cassie, Wenzel, these 2 terms should make perfect sense to you. You should now understand what is Laplace pressure, photoresist, nano imprinted lithography, soft lithography, duetting, and this picture should always remind you of an AFM. So, with that, I thank you all for attending this course from my team here, along with my TAs Nandini and Anuja, and I really hope that you enjoyed this course. Thank you very much from IIT Kharagpur.